Okay, it's me again with a new lecture. This is going to be longer than the past one. The thing I want to do is actually revisit, the divide, or so-called divide between old and new quantum theory and wave mechanics, and I will do so by revisiting the papers, presentations, and more particular the discussions at the fifth Solvay Conference in 1927, which was quite a watershed indeed. I will briefly pull them up, but I want to be careful to respect copyright. But here you can see how they look like. They're in French only. I haven't seen really like a good translation in English. We need to remind ourselves that the working language of many physicists at the time was French and German. That's probably also why Dutch physicists like de Bay and Hendrik Anton Lorentz, about whom I will speak shortly, were pretty much involved. So English wasn't the lingua franca of science at the time. I'm briefly gonna show. I think I do respect the terms of use of these. A bit like on DI fusion. You shouldn't really. You can reference, but you shouldn't really copy large parts of it. I want to show the interesting thing is that this was the last Solvay conference where Hendrik Anton Lorentz, and this is want to show because it's kind of sad, was the chairman and also joined. He died a few months later after attending from what was probably Saint Anthony's fire, an infection by bacteria now, which can be cured by antibiotics nowadays, but at the time it was mortal. So it's kind of funny that you have, and sad at the same time, that you have this letter and picture in black, regretting the death of Solvay, while Mr. Lorentz was probably the most active participant, especially in the discussions of that council. I want to immediately. I have a blog for those who know me, and it's called readingfeynman.org. I should probably rename the website because it's not about Feynman, or if it is, it's more to disagrees with his particular interpretation, I would say, of the math, quantum math, in a number of places. But so the last words of H.A. Lorentz, I have a paper on sort of the old quantum physicists, Lorentz and Bragg and Sommerfeld and Rutherford and Larmor and a whole range of others, Einstein, of course. Sort of juxtaposing them against the interpretations of at first Schrödinger and then Bohr and Heisenberg, reinforced in that sort of quantum math. We only want to calculate probabilities, and these probabilities are not necessarily rooted in physical processes. So the last words of H.A. Lorentz, at least at that Solvay conference, and here I do quote it in French. You can translate, but I will just note something that has driven me is it's not necessary to elevate indeterminism to a philosophical principle. I think that's a beautiful statement. My worldview is a statistical determinism. I think of charges and fields and oscillations, linear oscillations, orbital oscillations of charge, linear oscillations of fields, and the frequencies involved are very high. So and we don't know the initial conditions of the oscillation. So this phase differences there that we need to work with. And as such, I think new quantum mechanics and the whole framework of modeling probabilities and energy states has contributed to a better understanding. But I do believe that there are physical processes underneath everything. So that's about Lawrence for that conference. And as said, yeah, we'll talk a little bit about, I will first talk about the very first paper is actually an example of, I would say, old theory, old quantum theory. And that's by William Lawrence Bragg, who is really well known from his research on crystal structures with the help of X-rays. X-rays are have high energies, and so the idea is that if the electron, if electrons in a crystal structure, if you shine X-ray light on them, if they will absorb or reflect or diffract X-rays, they will only lose they will do so when giving back the full energy of the photon, or almost the full energy. So that's the title, l'intensité de réflexion des rayons X, the intensity of reflection of X-rays. William Lawrence Bragg, he was the youngest Nobel Prize winner ever. He was 25 when he received the Nobel Prize, together with his father, who was and when he presented this, still doing research in the same fields, you know, X-ray diffraction, and thereby discovering crystal structures, how they work. Bragg was not an American; he was an Australian-born British scientist. If you look at the participants of Solvay Conference, it's only after the Second World War that you see a lot of Americans coming in. Of course, Arthur Compton is there in many Solvay conferences between the two world wars, but mostly it's a European affair. I insert this beautiful image from the article on Rayleigh scattering, Wikipedia. Rayleigh scattering is complex, and the complexity is shown here. We have a piece of glass, and as you can see, this piece of glass, because of its crystal structure, scatters more of the blue light, so it looks blue. And at the same time, the photons with a lower frequency, lower energy, yellow, orange, red, they seem to get through, because the intensity, the scattering is less for these lower frequencies. And that's something that I want to immediately draw attention to, that you don't find in you know, the law of scattering as described by Thomson scattering or Compton scattering. No, there is a factor there. Scattering processes are very complex. I'm gonna talk about that. It's very difficult to model them, and yeah, to incorporate a model which accounts for different scattering intensities, with including the variable of the frequency, the energy of the photon. That's something you won't find. I explain here, I put a few notes. For light of a very specific frequency, we have Bragg's law. I will talk about that. I know it here. That's a condition, Bragg's condition it's called. I'm going to talk about that. If you want to see the derivation, I will talk about that. I will take the Wikipedia article on it, but you can also have a look at Feynman's lectures in volume 2, lecture 30, and also actually new, I mean, effective field theory. I kind of like it. It's sort of a probabilistic framework for analyzing things, and they start actually with exactly explaining this phenomena. Why is the sky blue, or well, why is this crystal? Why does it appear blue? So that effective field theory, and that's kudos to modern quantum mechanics, is one that does explain, I would say, the intensity of reflection by using a factor, the frequency to the power 4, that is incorporated into the model of reflection or scattering. That may sound like Chinese, so I'm gonna have a more intuitive appraisal of Bragg's contribution, the very first presentation, and a very useful discussion that follows. I will quickly pull that up again. It's quite it's long. Here it is. I think it's about 40 or 50 pages, and the discussion is well, is included from the 300 plus pages. This presentation by Bragg of what formulas we have, how reflection would work, is definitely an example of old quantum theory, I would say, and so I'm going to talk a bit about how the how Pauli, react to that. What is striking in the long presentation of Bragg is first it's filled with graphs and illustrations from empirical research, and that's something you do not often see in modern articles on quantum math. It's all math, and they sort of often forget to relate it to the real world. He talks about how he experiments with a very wide range of crystals, rock salt, but also salts of aluminium oxides, aluminium silicates, alums. And that's sort of something I really appreciate, and why it's nice to read those papers. It's lacking in most modern day articles on quantum mechanics. Math has become apparently more important than the physics I write here. The second thing that strikes me in Bragg's contribution is he presents these very simplified models and equations, Bragg's condition for reflection, about which I will talk, and then a formula for the intensity of the reflected light. He's throughout the presentation, he's very consistent about all and talks about all variables that might be relevant, and that's not only the structure of the crystal and possible impurities or in the crystal, or imperfect structures that get broken because the crystal formation isn't perfect. But he also talks about the impact of temperature on the intensity of reflected light. He talks about polarization coefficients of incoming light, and a lot about a lot of other stuff. It's kind of amazing because the experimental devices then that's also interesting to read. You have the use of photographic plates or film, photographic emulsions. You had luminescence screens, fluorescence. I mean, Röntgen is really interesting. He uses cardboard and coats it with the barium platinocyanide. I don't know what that chemical is, but it makes the cardboard fluorescent. And that's how he discovered X-rays. Cloud chambers were already invented, but they were... it was only, well, this is 1927. They were only like fully developed in the 1920s, really. The sources of light at the time, it wasn't lasers, it was light bulb filaments, gas tubes, Crookes tube, Coolidge tubes. I mean, these differ in their design. Again, I'm a Belgian, to note Philips Research Labs, the large... They were an important manufacturer of such tubes. The point that I note is that it's really amazing that these people in the early 25 years, the first 25 years of the 20th century, they were able to measure so much. I would say with so little. So I said it again, Bragg's contribution to the 1927 Solvay Conference may be thought of as old quantum theory, and you can feel some of the antagonism between, the young wolves led by Bohr. But that antagonism, that's something I highlight also in my blog. You know, it's a bit scientific lore, so it's untrue that the 1927 Solvay Conference was like a battlefield between Heisenberg and Einstein. The papers and write-up of discussion actually reveal that Einstein hardly intervened. Perhaps he was tired of the discussions. We must also note that he had boycotted the Solvay conferences immediately after the First World War because the organizers boycotted the German scientists and he thought they should be invited. And so they weren't, and so he refused to come. But so these battlefield stories, such as Heisenberg telling Einstein to stop telling God what to do, I looked for that, or Einstein then declaring God doesn't play dice. They're like popular hearsay, I would say. Heisenberg and Einstein didn't say that, not at the occasion of the 1920 Solvay Conference as captured. In these papers and discussions, what you see is actually very nuanced and deep philosophical statements said on both sides of the so-called divide or schism. And that's what I want to explore in this and other lectures, that, statistical determinism and what these new quantum theorists came up with, it is not incompatible. Just to note, it is true that there was a tension. Language used by Bragg was when he wraps up, he talks about diffraction, he also talks about refraction. He said that he presents it as un autre exemple du succès de l'application des lois classiques. So he really says that, the laws that we have, and he's talking about Planck-Einstein relation and stuff. They explain things very well. There is no need for an assumption of, approaching things only in terms of probabilities. So all in all, he presents a very complete overview of scattering theory, I would say, which go much beyond the simplicity of the things you've learned in introductory courses on physics, Compton and Thomson scattering formulas. And then you have the discussion. Again, I'm going to quickly pull that up. I hope that's consistent with the terms of use of these. Yeah, I think I'm here with the. So there's a really long discussion. That's the discussion on the Compton report. Well, yeah, I would need to look it up. But after each paper, you have a long discussion. What strikes me in this one is that the first intervention is made by Peter de Baay. It was a Dutch. His life has been a bit controversial. When he was in Germany, and anti-Semitism was on the rise. But in any case, he there's stories that he was like a spy or something, or a Nazi. These are probably untrue. You can look it up on Wikipedia. Very interesting guy. But he starts immediately with a discussion, on thermal energy in a crystal structure as a scattering variable, and he also talks about. He asks really, would it be possible to imagine sort of a zero energy state in crystal structures for the electron, for the atom? So that's interesting. Goes back to superconductivity and whatever. So I'm not going to go in detail, but it sort of gives an idea of what kind of questions were raised. There's an intervention by Ralph Fowler also, who immediately sort of refers to les fonctions de Schrödinger. Schrödinger's wave function or probability functions, and Heisenberg jumps on that and to claim that these offer a much more precise result, the résultat exact, in terms of explaining how scattering works. In case how you get these intensities of reflection. Wolfgang Pauli makes an interesting contribution. It seems random at first. He says basically, in the theory as Bragg presents it, it is a pretty classical idea of energy densities, charge densities in 3 dimension, and he writes that up as a bit of a wave function, as a function of x, y, and z coordinates. Why he basically says, when we're talking densities, we need to realize that atoms consist of many of particles, electrons and proton. And he immediately talks about the number of particles in an atom and the number of particles, the number of atoms in a crystal structure, and says, one of the paradigms of new quantum physics that when you have a wave function, you should incorporate n times 3 coordinates for with n being the number of particles that you study. So I will explore that in later papers. Pauli also makes contributions to the what Born and Schrödinger present. So I'm gonna leave it at that. I wanna talk about scattering. So here basically you have that comes from Wikipedia. I need to acknowledge the source, but Bragg's law for diffraction, which is n times the wavelength of an incoming photon is equal to 2 times the distance between the atoms or molecules that make up, the atoms basically that make up the crystal structure. I presented here an early was called copper sulfate. You can immediately see that a crystal structure is a complicated thing. I mean, making a unit cell with these kind of complicated molecular structures in a crystal is not as evident. But simplified, we could say the condition for light to be reflected is that incoming light comes in at such an angle that the wavelengths when the photons, the individual rays, are reflected, that the distance between the two trajectories is the difference between the trajectories is equal to 2 times d times the sine of the angle of the incoming light with the plane of the crystal structure. Here you can sort of see the experimental setup. I want to immediately note that this is a figure from Low, which shows that reflection pattern. As you can see, it's not only the polar angle that counts, but also the azimuthal angle. You see here also there's in certain angles, certain azimuthal angles, there is no reflection whatsoever. It's zero, and it's only at specific points here that we have this intensity, this high intensity, this positive interference or constructive interference between photons or rays. Still, it's kind of remarkable. You get such an remarkable geometric and fairly simple diffraction pattern. And so that's the Bragg's condition. To show how Bragg's condition work, I mean, I always recommend that a little bit. I use Desmos. Here I write the inverse. If n times the wavelength is equal to 2 times the sine the angle, then the angle for which there is positive interference will be the arc sine, the inverse sine of the inverse of the sine function of that quantity n, with n being the order of diffraction, 1, 2, 3, or 4, and the distance, the interatomic distance, the wavelength. And you can sort of see that's the red line. That sort of it gives a unique solution, and there's only a reflection at one angle for these distances and that wavelength, which is chosen randomly. As you can see, the intensity of radiation according to that, the angle, there's several angles that go with it depending on the order of diffraction. Different angle, different order of diffraction. Now the intensity is the second function. The Planck function is given by, let me go to that. I said with the X-ray diffraction, we're assuming Thomson scattering, elastic scattering, no energy get lost. And that's the formula I'm going to talk a little bit about It's kind of a curious formula because you've got a factor here that is there, 1 plus the square of a cosine and 2 times the angle. This is scattering for one particle, and then we have this factor here, which is a weird one, which I'm going to talk about, and it's proportional to the intensity of the incoming beam. Now, this factor is let me go, a factor that oscillates between 0.5 and 1, and that's kind of funny probably, but I'm going to show you how we get there. You would expect sort of a factor that shifts between 0 and 1, but that's not the case. We could bring it we could bring it to an interval from 1 to 2 if we would take out the 1/2 factor. But yeah, I mean, the result is basically that you have 2 times the incoming angle, so you've got a cyclical thing with a cycle being equal to 180 degrees or pi. Now, the second factor here is an interesting one, and I'm not going to go into much detail, but it's one that is puzzling. It comes out of very classical mechanics, but you've got this factor between the brackets, which is the square of the electron charge divided by the energy of the electron, and so that has a weird physical dimension, Coulomb squared divided by Newton meter, Joule, and if we take the square, it's 4th power and a square. And what I do here is a little bit, you would expect, okay, this energy, you can say there's an energy density, a square of energy is going to be some energy density of the electron. The charge inside, I said in my realistic interpretation, which is the Zitterbewegung interpretation of quantum mechanics, the charge is all packed into the Zitterbewegung charge, which has a very small but not infinitesimally small size, which is given by the fine structure constant times the Compton scattering radius alpha times h bar divided by mc. And I wrote a lot about, I have a lecture about the interpretation of the fine structure constant. There's various, it's a scaling factor, which is inherent also in what I write here. We have a Bohr radius of an atom, and we have a linear wavelength of a photon. We can write that also as a radius, a reduced wavelength. And alpha, the fine structure constant, as a coupling constant for electron-photon coupling, can remarkably be written as the ratio between the Bohr energy, the energy of an electron in some atomic orbital, times, divided by the ratio of the reduced wavelength of the photon and the Bohr radius. I show that here, I write it all out, that's classical Bohr model. And that's sort of where, rewriting this factor here, as I do here, q squared divided by mc squared, is you can actually write it as the Compton radius, I said h bar times c divided by the energy, or h bar times mc squared. And you get this alpha divided by the Coulomb constant in addition. So this factor can be written as something weird. I don't have an intuitive explanation for that, as a fine structure constant divided by the Coulomb constant times the Compton radius. But you can immediately sense that, yeah, this factor here has to do with scales, with a ratio between the classical or Thomson radius, the hard scattering radius, I would say, of the Zitterbewegung charge inside of an electron, and the radius of the electron as a whole, or the radius of an electron as it oscillates around a nucleus. So again, this will be Chinese, and I will go straight to my theory of scattering. This talks more about how you derive a Thomson cross-section, and then I will go back to this is a bit my theory. So my model of an electron is that it's a ring current, so which actually goes in the other direction. It moves into the screen and it comes out here, and so it goes round and round and round, and here we have a sideways view of the and so how should we imagine a photon that comes in? I think there's 2 or 3 situations we can imagine. indeed sort of an incoming photon that hits that Zitterbewegung charge directly. What happens there is that the electromagnetic field becomes a force because it acts on a charge, a point-like charge. The charge is gonna oscillate. It's gonna go into yeah, it was in an equilibrium situation and it was spinning around the nucleus in some kind of atomic orbital, but now it gets an extra motion, extra kinetic energy, so there's this equilibrium there, and it's going to return to an equilibrium state by emitting out another photon, probably or maybe not so probably, I don't know, with the same frequency. If this is sort of the difference between Compton elastic scattering and inelastic scattering, is for me really your idea on what an electron, you know, where it is, in which energy state. Is it a bound energy state? Is a free electron, I think, is a hypothetical theoretical concept. Electrons and crystal structures, they are tightly bound, or somewhat less tightly in atomic and molecular structures. So that determines sort of what I would say the degrees of freedom and what kind of and how they absorb energy, possibly in thermal energy, or by emitting infrared radiation, which is sort of giving the thermal energy back, or causing, you know, just the target as a whole to move in a certain direction, getting some kinetic energy. So that's the first interaction. The photon interacts directly with the charge, and so I said the electromagnetic field then acts on that charge, causes a disequilibrium, and this energy is radiated back out fully, or yeah, a little bit inelastically. Maybe there is some loss of energy in the structure. So I said indeed, because strongly bound electrons, they cannot change their energy state. You know, they will have to return, and then sort of then I think the electron-photon interaction will be elastic. So I think this direct interaction is probably Compton scattering, but I said I wouldn't make the directly. The second way of interaction is that the photon will interact with the electromagnetic field of the Zitterbewegung charge, or the electron as a whole. That's here. We have a very dense magnetic field, a uniform. This is what goes through a ring current with the south and the north pole here, and you apply the right-hand rule. Always forget that the right-hand rule assumes that we are talking about a conventional current direction, so we think of positive charges rather than negative ones. For negative charges, we need to reverse the direction of B. But this would be the third thing, that sort of, yeah, the incoming photon here messes with that electromagnetic field that keeps our Zitterbewegung charge in place and spinning around. And yeah, there again, there is a disequilibrium situation. The electron as a whole will return to equilibrium, and so I put here backscattering. Maybe not necessary. Maybe it will go through. I don't know. But here I just, for some intuitive reason, I think it's a backscattering. Intuitive reason, I would say, you know, it will absorb some. You know, the magnetic force tends to give a pushing momentum to charged particles, and so there's going to be yeah, pushback, I would say. And so that's where I think that the kinetic energy or the pushing momentum first goes in and then goes out again. So that's where I think we have a backscattering. But that's just an intuition. The third thing, possibility here, and that's one I'm not so sure of, but it's sort of because you have these factors in the Thomson scattering radius, and they're give the impression Thomson scattering and also Compton scattering may be a little bit larger than the theoretical Compton radius of an electron. And that's where I don't exclude that a photon might actually, you know, we have a much weaker magnetic field as we move away with field lines that are becoming far less dense. But very close to the ring current, yeah, the electromagnetic field or the magnetic field of this ring current is very strong. And so yes, there may be a threshold value where again the photon sort of gets absorbed, causes this equilibrium situation, and when the system returns to equilibrium as a whole, a photon gets emitted out again with same or probably a slightly lower frequency, lower energy. So these are the three modes of interaction, and you can quickly see that it's going to be quite complicated. The variables are indeed, you know, the polarization directions, both of the photon and the electron. It oscillates in a plane. It's a 2D oscillation. So you have a polar and an azimuthal angle for this plane of oscillation, or for the electron. Also for an incoming photon, you know, this polarization direction, which we can describe again in terms of you know, polar and an azimuthal angle. I said the degree of elasticity of the absorption and emission process is going to depend very much on how much energy the system can actually absorb, and how and why and where it goes. Is there really effective absorption that gets lost in thermal energy of the system as a whole? These are very difficult questions to answer. And so the Thomson scattering, Compton scattering, I would dissociate that this discussion a little bit from these, I would say, these modes of electron-photon interaction that I identify here. It's just to explain, because now I'm going to go to the formulas, that when you see a formula like this, this Thomson scattering, take it with a grain of salt. It's really explaining a process. It's not necessarily what happens in reality. To bring things back to reality is, of course, that when you Google on ResearchGate or other open research forums, I want to solve it. There's a paper of last year by Chinese researchers who really do, you know, fairly basic stuff, and that's repeating these experiments that von Laue and Bragg did with copper sulfate, hydrated copper sulfate. The raw material, the powder, as you can see when you shine X-rays on them, the absorption spectrum or diffraction pattern or reflection pattern looks, we can see that at certain frequencies there is constructive interference. At other frequencies the intensity of the reflected light is 0, which means everything gets absorbed. 2 theta is the angle of when you make it a crystal, it becomes a much this is the powder. It becomes a much cleaner structure. You have this red graph here that I acknowledge, these are two Chinese, and then you have indeed a first, a second, if you look at the red, a third, a fourth, and a fifth order of reflection, and at other angles you know, there's full absorption, and they you know, the black curve, they do relate it a little bit to you know, copper sulfate in powder form. But as you can see, this factor that oscillates between 0.5 and 1, here it is between 0 and 1. So don't try to directly relate, you know, Thomson scattering formulas and Compton scattering formulas to this kind of you know, very intricate crystal structures that reflect. That's sort of where I put a bunch of things. I said wave function representation for me are not for the free electron. They are the equations of motion. We have a radius, and you know, the radius vector does give us the motion, which may be chaotic or not, of the theta beweging charge. For a free proton, we have an oscillation in 3 dimensions. So I use another imaginary unit, J rather than I, to show that the plane of oscillation oscillates itself. We have a factor 4 in a 3-dimensional oscillation. I talked about that in previous lecture. For a photon, we may have also a wave functional format. I put here an electric plus a magnetic field vector. I don't know if that's mathematically really correct, but we know that the magnetic field vector is its magnitude is 1 over c times the magnitude of the electric field vector. And I said this is a main symmetry. The electromagnetic force is right-handed or left-handed depending on your convention, to look in the direction of propagation or reverse direction. But you could write it as the electric field vector minus the imaginary unit as a rotation factor times the electric field vector divided by c, and so you get something like that. And then for the electric field vector you could write a wave function, you know, the frequency of the photon times t times the imaginary unit. But never forget, a photon is a traveling field, It carries no charge, and it's not because the magnitude of the magnetic field vector is so much smaller that that's essential. This propagation mechanism, you may think of that, a curl or a flux of the electric field vector causes a change in the magnetic field vector time variation, which again causes a change in flux current or curl, and that's good. And in the Bragg equation, you have the same mechanism at work. That's where I pretty much believe that my intuition that Schrödinger's equation models motion rather than only interpreting as something that gives rise to probabilities. Of course it does. If an electron spends more time at one place than at another, the probability is going to be higher. But that's sort of my interpretation, that the probabilities are rooted in equations of motion, as Dirac termed them. And but yeah, these equations, I mean, here, this is a figure I took from Wikipedia, I think. This is a polar graph, I hesitate, it comes from Feynman. The motion inside of an electron, inside of an atomic orbital, may be very complicated. This one actually is here sort of tentatively showing this rosace, as Lorentz called it. Yeah, an electron is going to have, it's going to precess, and all kinds of factors come into play, which makes trajectories very complicated. That's what I put here a little bit. Think about rotations within rotations and multiple frequencies. It's not an easy thing to model what is actually happening when an electron and a photon interact with each other. So I'm kind of done with the theory. What I just want to present is, let's go back to the Bragg's equation. Again, very briefly, I'm not going to go into that, but this formula for Compton scattering, this one, we and I'm going to show it to explain the equation that Bragg starts out with. It is rooted in a very classical radiation model where we think of incoming light that has, the electric field vector has a radial component in the plane of this diagram, or this comes from Wikipedia, and then sort of it's gonna give, it's gonna make the charge also oscillate sideways as we look at it from on top of that. Our direction of viewing is not this one, but 90 degrees to the observer that is here. The observer here is in the plane of this diagram. And this radial component, as the observer sees it, will be, only a cosine of this angle between the incoming and outgoing wave. We're not thinking about photons, we should, but we don't here, in this very classical derivation of the Compton scattering radius. And of course, the factor that I can't really draw, that there will be a tangential component. Tangential, what do we mean? It's perpendicular to the plane of this diagram. So as you are looking to the screen, imagine a vector of motion going in and out of your screen. And that's the tangential component. And of course, that's going to be the same for us as for the observer. So we don't have a cosine factor here. So the tangential component, no sine or cosine factor. The radial component, yes. And then, this is geometry. These 3 divided by 16 pi factors. But that's the thing. We think about emission coefficients, 2 emission coefficients. We integrate. I talked about the complexities of calculating a cross-section, talked about what a solid angle is and all these kind of things. But you get something like that the total energy that is radiated out through the various angles where there is a reflection should be n times, the cross-section. There are n electrons in a certain atom, times their cross-section, that's the total surface area, times, an intensity per unit area. So, the formula makes sense, but yeah, of course, this formula does not take into account, indeed, a reflection and full absorption. Perfect crystals should not be absorbing any light, but what is a perfect crystal? Do they exist? Diffraction and reflection, there's also refraction. Wavelengths may change slightly in energies when passing from one medium to another. It's a very special phenomenon that you have in wave mechanics, and it may apply to photons as well. So according to Bragg, he warns for that. This produces de légers écarts à la loi, at Bragg's law, where the angles of reflection should respect this law. The point to note is that I know you probably switched off. I'm gonna see. I've been talking for 45 minutes. That's okay. I'm almost finished. Yeah, many real-world effects are there. One example that William Lawrence Bragg gives is that his father measured how intensity diminishes, and he did it with diamond crystals. It's expensive experiments at the time because you didn't have any artificial diamond. When you heat them par élévation de température, Debye predicted that, and Lowe observed that. So there's an impact of temperature on the intensity, and so that doesn't capture. And Bragg admits that. He said, there's a lot of different formulas for the intensity of reflection that we could try to present or invent and see if they match real life intensities when doing experiments with rock salt or aluminium oxides or whatever crystal structure, lattice structure. He says, je ne donnerai ici qu'une seule des nombreuses formules dont son densité. Elle montre bien les caractères essentiels de tout. So he admits that the formula he starts off with, which is this one, is just one of the many formulas you can have. And I use it because I want to encourage you to sort of read these discussions, go into the papers, see the subtleties of these arguments of these great scientists. Almost all of them were Nobel Prize winners. That changed when they still Solvay conferences, but they're not what they were between the two world wars and just before. The first one was in 1911. But yeah, you have a sort of an intensity. You have that factor that goes between 0.5 and 1, that interval. So that formula pops up there. Does it make sense? Not sense? I don't know. But then instead of that Q square divided by MC square to the power 2, he gives this quantity Q and 2 times mu. So the structure of Bragg's formula for scattering is quite the same. The difference is that he calls this the factor of polarization. I said we see it in the Compton scattering formula, the modern one. And he says, yeah, that basically takes into account that les rayons incidents ne sont pas polarisés. We can have all kinds of polarizations of incoming photons, and so that's the factor that takes it into account. Okay, it's a good interpretation. The Q is, I'm going to talk about it first. He says there is effective absorption, and he takes it immediately into account by putting a coefficient of absorption, effective absorption there, which will depend on the material, the crystal structure, and so many other things. Now he says then, and this is the monster, which I'm not going to analyze this here. So the thing we need to explain is this Q, and he sort of puts in there the number of particles in a crystal per unit. A density, a three-dimensional cube or per volume element. The square of the electron charge is there again. We have the MC square factor that we saw in the classical derivation of the Thomson scattering, but we also have this factor F, which he explains that, and then we have this factor, which honestly, I think that comes out of the Bragg condition. Looking at its form or shape, but I will be honest, I would need to see where it comes from. But he says F est la quantité que nous cherchons à déduire. Elle représente le pouvoir diffusant du cristal. Crystal is without an H, I think. Yeah, Mesurer en fonction du pouvoir diffusant d'un simple électron. So there he tries to find a factor, and this is where, as I argue in my paper on the concept of the Bragg's wavelength for matter particles, for elementary particles, there he this is a bit sort of the mystifying factor that everybody was looking for, and it can be found, according to me, into the to accepting that first an electron has an internal structure. It is a ring current with a hard charge inside. But so you can see, and this is interesting about 1927 and Bragg's intervention, that that's sort of the holy grail they're effectively looking for. You know, an explanation for the reflecting of diffusing power for oh yeah, I clean it up and then crystal is back with an H. Mesurer en fonction du pouvoir diffusant d'un simple electron. So they try to explain it in terms of you know, yeah, the structure of one electron. In my humble, in the reinterpretation, I would say, of Bragg's lecture and other papers that are in these Solvay conferences. So I'm gonna leave it at that. I probably this video is not gonna be as popular as others because it's probably it sounds a bit like rambling. But yeah, I may write this out in sort of in what I said at the beginning of my lecture, a bit of a reappraisal of this schism or probabilities, you know, models that I used to explain, you know, something which is very beautiful here, a glass crystal that appears to be blue, just like the sky appears to be blue. You know, a model that takes many factors into account when it talks about, when it tries to analyze how electrons and photons actually interact. So that's it. I'm gonna upload this as is, and I said I should probably prepare better, but these videos help me to make sense of my notes in this little notebook, and then maybe write a paper about it as part of, I would say, maybe a series that I'm gonna do on these Solvay conferences, and pointing out where I think things went a little bit wrong in terms of interpretation. So I thank you for listening. I know retention rate of my videos isn't very high, but I think many people also download papers on my research. Let me Google that and show you that, because I do on my ResearchGate page. There's a lot of reads or a lot of downloads, I would say, but yeah, maybe people do only read a very limited part of the papers. I want to show you one in terms of these models, and that's the original paper with my indeed realistic interpretation of the wave function, or the Bragg's wavelength. It's gonna pop up, I think. Here, the Bragg's matter wave, the concepts and the issues. I wrote it in 2020. I think it shows the importance of thinking indeed that of electrons and protons as having a structure, thinking of them as being oscillations of charge, nonlinear oscillations, orbital oscillations. So we have orbital frequencies, no linear frequencies, and then everything sort of comes out of it. We can have a wave functional representation of electrons and protons that makes sense, literally a representation of how they move in space, and then we understand the Schrödinger's wave equation much better as a relativistically correct one. And then I talk about Dirac's wave equation, why these assumptions that he has aren't probably not correct, and therefore give rise to these infinities and runaway electrons and whatever. So that's it. I wish you a very nice day, and